Buenos dias. At least I've said something in Spanish now. Thank you for that kind introduction, and I'd also like to thank the organizing committee for inviting me to come to this wonderful location and this very well organized and interesting conference on green chemistry. I particularly would like to thank Santiago Herrera, who is director of the scientific committee, for inviting me. So I'm very pleased to be here in Mexico City. This is on, yeah, because I may want to walk about a bit. I have altered the title of my talk slightly. I thought that this was a better title for a conference in a department of chemical engineering on green chemistry. So I made my title Engineering a More Sustainable World Through Green Chemistry. You see. So therefore, I invented my E factor. And well, as I'd worked in the industry for quite a while, I knew I had a lot of the data to be able to do some calculations here. And what I saw was that in bulk chemicals, the waste can be very low, but it also can be a few kilos per kilogram of product. One example is caprolactam. DSM, where I worked in the 80s, produces caprolactam, a bulk chemical using a process that produces 4.5 kilograms of waste per kilogram of product. As we go downstream to the fine chemical industry and pharmaceutical industry, the E factor goes up very quickly. One reason for this is the molecules are much more complicated, so you tend to get multi-step syntheses, and that would make more waste in general. But another point is that it's because they're using stoichiometric processes. And another thing I'd tell you is, over the years, because this was published, I published this table first in '92. Over the years, I've given many talks to industrial audiences where I showed this table. And I can tell you one thing, that nobody ever objected to these numbers. Nobody ever said, Roger, they're too high. So what does that tell you? They're probably too low. And now the chemical industry, and particularly the pharmaceutical industry, is using my E factor table a lot. And here you can see a quote from Chemical Engineering News 2007, which I was very pleased with this lady, Anthea, saying this. Another aspect of process development mentioned by all pharmaceutical process chemists who spoke with CNN is the need for determining an E factor. So, what is the E factor exactly? It's everything but the product. So everything you're making in that process, well, not just making, using. So it's the actual amount of waste formed in the process, including solvent losses and waste from energy production, really, as well. So it's different to atom utilization, which is a theoretical number. So the E factor is also kilograms of raw materials minus kilograms of product divided by kilograms of product. So you can easily calculate this for a process or even for a whole company. And I calculated the E factor of our company. We were a fine chemicals company. I calculated the E factor of the whole company back in the 1980s, and our E factor was 20, which was not that bad. And you can, for a company, you can easily find out what it is because you go to the purchasing manager and you say, how many tons of product did you buy, or tons of raw materials did you buy last year? Then you go to the sales manager and you say, how many tons of product did you sell last year? And if you've got those two numbers, then you can calculate the E factor for the whole company. And I'm surprised that a lot of companies don't do this. Why don't they calculate what the E factor is for the whole company, and I can tell you Pfizer does that. Pfizer has calculated what the E factor is for the whole company, and they have a program to reduce the E factor over the coming day. This is the petrochemical carbon cycle. You're starting from sunlight, you're making plant biomass, and then which eventually becomes oil. In an oil refinery you make fuels and chemicals, and via combustion of the fuels you get CO2, and the whole cycle starts again. So it is a cycle, but the problem with this cycle is, of course, it takes too long. It's like the evolution. You will get a better enzyme, but it takes millions of years. So the petrochemical carbon cycle is just taking too long, of course, around here. So what we need is to balance the carbon cycle using, for example, industrial biotechnology. So now we're making the plant biomass, but we're putting that plant biomass directly into the biorefinery. We're making sugars, and via industrial biotechnology we're making fuels and chemicals and completing the cycle. But now, instead of taking millions of years, this is something that can just take a year or less, or well, maybe a year or a couple of years, let's say that. So what we're talking about here is the bio-based economy. And in the bio-based economy, we don't want to use first-generation feedstocks like corn, because we're competing with food. So what we want to use in second-generation biorefineries is inedible plant oils, algal oil, waste oils and fats, whole agricultural crops, or I would say waste in general. I think this is the future. The new frontier is using waste, using something that is just being thrown away now, and especially waste biomass, waste lignocellulose. This is the raw material of the future. And so from those raw materials we go to various feedstocks: triglycerides, lignocellulose, terpenes, proteins. And the lignocellulose can be converted to hemicellulose or cellulose plus lignin. They're interconverted. This can be converted by hydrolysis and fermentation to terpenes. There are companies doing this. Or you can even convert cellulose to triglycerides if you wanted, using oleaginous yeast. So most of these feedstocks are interconvertible. Waste biomass is the new frontier, I would say. And look at the numbers we're talking about. Lignocellulosic biomass residues. Here, just rice husks alone, 120 million tons per annum. Sugarcane bagasse, 220 million tons per annum. Waste straw in China alone, 600 million tons. All of this is burnt. It's just burnt off. What a terrible waste of a raw material. Orange peel in Brazil. I don't have anything for Mexico here, but I'm sure there's some waste biomass that's being produced. 8 million tons of orange peel produced annually in Brazil. Now look, I tried to show you here. One of these is 5 million tons per year, and a big bag is 50 million tons a year. Here we see transport fuel. Going to be very difficult to make all this from waste biomass. Very difficult, but not impossible, I don't. But look at the bulk chemical industry. We could easily make all of bulk chemicals from waste biomass, quite easily. And so I think that this could be the future. Maybe this will replace PET. And interestingly, Avantium has a cooperation with Coca-Cola and Danone to make these PEF bottles. Obviously, Coca-Cola has the money to do it, and they are not betting on horse here. They're betting on at least 2 or maybe 3 horses for the future here. So I just wanted to wind up with coming back to the same question is, how do we know when it's sustainable? We can talk about it being sustainable, but how do we know? How are we going to measure that? And within the EU, we have something which is called COST, and that stands for Cooperation in Science and Technology, through all the 28 EU countries. And COST has projects where they try to get all the 28 different member states cooperating with each other. And they have a COST project, utilization of biomass for sustainable fuels and chemicals, biochem. And I happen to be the chairman of this project. So, and one of the things we're trying to do in this project is to come up with a set of metrics to measure the sustainability of bio-based products. Or, as we've said, to shape a unified view and metrics for comparing different processes to sustainable fuels and platform chemicals from biomass. And what we've done is we have selected 7 products, these 7. And we are comparing the petrochemical processes to make these 7 compounds with the bio-based routes to make these compounds, and trying to see if we can come up with a set of metrics which are meaningful in saying which one is better, the petrochemical route or the bio-based route. In which cost is one of the items used. So it's not just an academic exercise, we're also using the cost of the raw materials and the process to do this comparison. Now, for the last 2 slides, I want to come back to what I started talking about, fluorolucinol. Why don't you make fluorolucinol using a bio-based process? In fact, it can be done from glucose. You can ferment glucose to make fluorolucinol. And these people here have done it. And unfortunately, it's not yet commercially viable. But that's probably because this product is only a few hundred tons a year. If this product was 10,000 tons a year, I think it would already have been optimized. And what about another possibility is you could make it from citrus waste, like orange peel or any citrus peel. Because citrus peel contains this molecule here, which is glucose attached to a fluorolucinol. You can enzymatically hydrolyze this to get fluorolucinol and glucol. In actual fact, I discovered recently that in the industry, they use this as a marker for testing the quality of oranges. So, what is the take-home message? It was obvious that a new paradigm was necessary for efficiency in organic synthesis. Green chemistry, catalysis and renewable raw materials merged science and technology with environment and economics on the road to a sustainable society. And this especially for industrial people, the message, green chemistry is not only good for the environment, it is good for business. And the best is yet to come. I'd also like to acknowledge co-workers at Clear Technologies and co-workers at the Technical University of Delft that have worked on the projects I told today. You see, now and then I show a painting. One of the famous inhabitants of the city of Delft, where our university was Johannes Vermeer, the painter. He lived in Delft in the 17th century, and he's most famous for his painting of the girl with the pearl earring. There is a book and a film about it. But this is also a famous painting of Johannes Vermeer, the city of Delft. This painting is called A View of Delft in this 17th century. Interestingly, if you just concentrate on that bit. That is the west gate of Delft there. And this is Delft today. In the 21st century, that's the west gate. It doesn't look very much different to what it was in the 17th century. And of course, in Holland, wherever you go, there are canals and there are always a lot of bicycles. Notice these cars along the edge of the canal here. You have to be very good in parking your car in Holland, otherwise that car ends up in the canal. And Dutch people are very adept at parking their cars with just centimeters between the car and the canal. So I want to leave you with a take-home message, and the take-home message is think green. And sustainable. So, thank you very much. Muchas gracias.